If you haven't done so yet, please pause the video and attempt to solve the question on your own before listening on. To solve parts A and B, we're going to note the following fact regarding the tension in the string. So we can see that the tension in each string is half of the gravitational force that's applied on this mass, capital M, in the diagram. And that's because we can see from the diagram that the mass is supported by the two ropes. And so the overall weight of that mass will be evenly distributed between the two ropes. And that's why the tension turns out to be half of mg. Now, of course, the speed of the wave in string 1 would be equal to the following expression, which we've learned from this chapter. We'll go ahead and plug in the expression for the tension that we just found. And then we'll plug in the known values for the mass, 9.8 for g, and then the linear density in string 1. And when we do so, we see that the speed in string 1 is 28.6 meters per second. Now for part B of the question, it's the same analysis. All we have to do is change the subscripts from 1s to 2s. And then we'll go ahead and plug in the known values. And we can see that the speed in string 2 is 22.1 meters per second. For parts C and D, we're going to set up two different equations for the speed of the wave on string 1 and string 2. Notice that these equations are similar for the speed equation that we used in part A. The difference here is that we don't have the factor of 2 in the denominator, because if we look carefully at the picture, each string is fully supporting the weight of its respective mass. So in other words, the tension in string 1 is now supporting the full weight of block 1, and the tension in string 2 is supporting the full weight of block M2. So we've included those full weights in the equation. Now, we also know that capital M is being broken up into two pieces, mass 1 plus mass 2. The question notes that the speed in the two strings is equal, so we're going to go ahead and set the expressions for speeds equal to one another. We will then square both sides of this equation. We could divide both sides by g. Referring to the second equation, we can solve it for M2 by subtracting M1 to the right side. We could then plug this expression for M2 into the equation above. We will then solve the equation for M1 by cross-multiplying. We'll distribute mu1 into the parentheses. We'll then add this term over to the left side so we can get the M1 terms near each other. We could then factor out an M1. We will then divide both sides of the equation by the term in parentheses. I suppose we could get a little bit fancy and divide each term by mu1. That way it will cancel from the numerator, and this term here will become just a 1. We could then plug in the known values for capital M and the two linear densities. And when we compute this, we get a mass M1 of approximately 188 grams. So that would be the answer to part C. Part D will be relatively straightforward because mass 2 is simply equal to capital M minus M1, which we just found. And when we compute that, we get a value of approximately 312 grams. So that's the answer to part D. Thanks for taking the time to watch the video. If you liked it, please click the thumbs up icon and subscribe to the channel. Also, you're welcome to send in your own question to the email address on the screen, and I will do my best to post a solution to it on YouTube.